So welcome to the Raja Umpire tutorial. I'm Robert Chen and I'll be starting us off. On the call we'll also have Christy Belcher, John Bowen, and Arturo Vargas speaking on other different parts of the tutorial today. In the chat we should also have other members of the Raja and Umpire teams to answer your questions, but they might be joining a little bit later. I'd like to remind everyone that there was an email sent by Christy this morning to set up your AWS instance so that you can run the code and follow along with our lessons. So I'll ask you to, if you haven't already, refer to that email and try to start that AWS setup process. One sec. Okay. So today our goal is to show you enough about Raja and Umpire that you can start using them in your own code development. We have more advanced features that will be covered in other versions of this tutorial. To start, we'll give a short high-level overview of Raja and Umpire. Then we'll go through the content of the tutorial lessons in the subdirectories. We'll end with a short demo showing a new feature where you can do performance profiling with Raja. And as usual, please don't hesitate to ask any questions anytime in the WebEx chat, or you can unmute yourself during the tutorial and ask a question that way. After the presentation, we'll monitor Slack to answer any follow-up questions that you have. So we value your feedback, comments, questions, and suggestions. You're always welcome to send us a message on our mailing list as well. Although the lessons today are intended to be easy and accessible to most people, we will still assume that you have some basic prior knowledge. For this tutorial, it's good to have a working knowledge of C++, including basic C++ template usage that you might find using the C++ standard template library. We also expect that you'll have a basic understanding of parallel programming on the CPU and GPU architectures, and that you've given some thought about how you'd like to parallelize an application that you might be working with already. So to start, the Raja Portability Suite contains 4 complementary projects: Camp, Raja, Chai, and Umpire. Camp provides template metaprogramming utilities and tools that are used in all of the repos shown here. Raja is a single source abstraction layer for performance portability, which allows codes to write one kernel that can run on multiple hardware platforms. Umpire provides memory management across different types of memory. And finally, Chai provides automatic data movement between different memory spaces based on Raja execution context. All 4 of these projects live on GitHub with documentation in their respective read the docs pages. The Raja Portability Suite insulates applications from programming model and hardware architecture details. Our suite is used in a variety of applications in the top row of this slide. The bottom row represents the wide range of CPU and GPU architectures that the Portability Suite is capable of running on. For example, we can run on AMD, ARM, IBM, and Intel CPUs. And for GPUs, we can run on AMD GPUs, NVIDIA, and Intel manufactured ones. So next we'll go over some basic Raja capabilities and concepts. Raja, as I've described, is an open source project with a growing user and contributor base. In the graph on the bottom right, you can see that interest has been growing in Raja steadily over time. So this is an example of a portable kernel execution in Raja. On the top left, there's a standard DAXP loop that you might write in C or C++. To transform it to a Raja kernel on the right, you can apply a for all construct in place of the for loop. The iteration space defines a set of indices to loop over, like 0 through n. And the loop body remains the same as before, but it's not contained, but it is now contained in a C++ lambda expression. And finally, the execution policy determines which hardware implementation will be used. So this is what happens when we use different execution policies highlighted in red within a Raja for-all. The Raja for-all will be compiled to a version of code that matches the architecture of the execution policy. So for example, on the left, a sequential policy will be compiled as a normal C or C++ for loop. In the middle, a GPU policy will be compiled to a GPU-specific blocking and threading. And on the right, an OpenMP policy will wrap a for loop with a proper OpenMP pragmas. Raja supports a variety of loop patterns, execution backends, and other types of transformations and utilities to help you port your application with minimal changes to your code. All the features in the previous slide are documented in the Raja user guide, which you can find on our GitHub page. We also have a proxy apps repo and the Raja Performance Suite repo, which contains a collection of kernels that you can use to assess compilers and performance of Raja. And of course, everything here is linked from the Raja GitHub project page. Next, we'll talk briefly about the basic Umpire capabilities and concepts. So Umpire works by coordinating things called resources, allocators, and operations to manage your memory. It supports a variety of memory types and has a lot of other useful HPC-related features, which the most commonly used is probably the memory pool. This is an example that highlights the need to use Umpire. On top, we need to use a variety of different calls in order to allocate memory for different types of hardware. So we have CUDA allocator on top, or a CUDA malloc on top, HIP malloc under that. SYCL has its own syntax for allocating memory, and OpenMP target has its own thing too. On the bottom, Umpire simplifies this by using a resource manager object, which is the RM here. You can use the resource manager to create an allocator on the underlying device, and then you can use that allocator to allocate memory in that space. And the same allocator can then be used for different backends. So Umpire simplifies all the variety of memory allocation that you could do. So all the features of Umpire shown before can be found in the Umpire user guide, which is also on the Umpire GitHub page. They also have an interactive tutorial to help you get started with Umpire, and a cookbook with common memory recipes to use with Umpire. And you can find everything here linked from the Umpire GitHub page. So we're about to get started with the lessons now. Just a quick note, we're offering tutorials throughout the summer on all of our Lawrence Livermore HPC tools. And you can sign up for other tutorials at the link shown here. So this is what I was talking about in the very beginning. You can follow along the tutorial with your own AWS instance, and you should have an email from Christy on how to get started to set this up. Just a note for people at Lawrence Livermore, the VPN will block you from starting the AWS instance in your browser, so you'll have to find a way around that. These are the instructions that you should probably have seen in the email. If you have questions about these things, you can write your question in the WebEx chat and we can give you a hand. And I think with that, I'll pass it off to Christy, who will talk about some of the basics of Umpire.
But essentially, this should be kind of your VS Code setup. And then, so I'm in tutorial, and then I went to this intro tutorial, and then lessons, and then we're starting on lesson 3. Because these first two are just kind of talking about getting your build set up, and just in the interest of time, we're going to skip to the interesting stuff. And that's going to start us off with this lesson 3. Also, so to build this, you want to be in this build directory, right? So I think when you first open up the terminal, um, you'll be in tutorial, and you just want to cd into build. And then if you type in make-j, you should see that everything is kind of pre-built for you. But yeah, put some kind of question or note in the chat if you are having trouble with that or figuring out where we are. But yes, I will jump in, haha, over here. Okay, so lesson 3, we are going to cover umpire allocators. When you look at this umpire allocator.cpp file for lesson 3, you'll notice there are to-do comments. I'm in the solution here, but we hope that you'll go to this other one and look at the to-do comments and kind of try to figure out how to fill things in. But essentially, this lesson will teach us about umpire allocators, which are the fundamental concept that umpire has for accessing memory. The allocator is just a C++ object that can be used to allocate and deallocate memory, as well as query things about the pointer that it's giving you. So in this particular lesson, we'll query the name of our allocator. But there are other things that you can query. And then we'll also see that the umpire allocator objects are created and managed by this resource manager. It's a singleton object, and in order to create our allocator, we have to obtain a handle. So that's going to look like this first line here. So we're just going to get the instance of our resource manager, and then from there we can do things like get an allocator. And when we get allocators, we get them corresponding to our desired memory resource. And this lesson will just be dealing with the host, so some CPU memory. And then when we actually want to allocate something with our allocator, the argument that we give it is the size that we want to allocate in bytes. And that will return a void pointer to that pointer, to the memory. And then the next thing that we will see how to do is how to use umpire operations. So moving and modifying data in this heterogeneous memory system can be a little tricky because if you're not using Umpire, you have to keep track of the source and destination memory spaces, and oftentimes they will have their own vendor-specific API. And when you do that, your memory management is not portable. And so with Umpire, we make that simpler. You can do all the data modification and movement regardless of the memory resource or platform through these Umpire operations. So we will look at how to do the memset operator. And just real simply, we'll set all of the memory that we allocate to 0. And then, yeah, after this tutorial, if you want to check out the documentation on allocators, there's a link provided. Also, I don't know if, we can provide a link here, but anyway. Okay, so I will just kind of show this in the solution here. Just don't forget to uncomment out this compile define. That just kind of makes it easier to have everything compiling when we get everything set up. But so definitely uncomment out this compile define. But then you can use the resource manager to get the host memory resource backed allocator. And then um, you can use that allocator to allocate 100 doubles. And it will be in this data pointer. And then you can use the resource manager to call the memset operation, and you pass in that pointer that is pointing to your 100 doubles, and then you want to memset all that memory to 0. Just keep in mind that this is a memset at the byte level. So if you were to instead put a 5 there, you would not be setting all of your data to 5. It does a byte level operation. But then you uncomment out this print statement, you deallocate your data, and then if you build it and everything looks good, you can run it, and you will see that we have allocated 800 bytes and set it to 0 using the host allocator. And yeah, so that will do it for lesson 3. If you have questions or anything, I can look at the chat. But with that, we'll move on to lesson 4.
So using what Christy just showed us, let's try to parallelize a basic for loop using Raja. So the type of for loop that we're going to parallelize is called a data parallel for loop or a data parallel kernel, and it's very common in HPC applications. And this is an example of a for loop that has no interdependence between the iterations. So it's operating on data, and those data accesses are completely independent of each other. This is also sometimes called embarrassingly parallel. And this slide has an example of how you would parallelize this with OpenMP, the simple pragma OpenMP parallel for statement. And we're going to show how you can do this in the same way using Raja. And this little diagram at the bottom just shows how how the parallelism is actually working. So if you think of M as the number of threads available to parallelize work, and we have an array of size n, then theoretically, if it takes t time in serial to perform this data parallel kernel using m threads, it should take t over m time. So, and that's just because there's no interdependence between the work, and if all the threads are working perfectly in parallel and there's no overhead, that's how long it should theoretically take. Now, in reality, there are real overheads to spawning threads and getting rid of threads. So let's get into that a little bit more with an example. So we showed this example with OpenMP. Here it is again. Probably, maybe some of you are okay or familiar with OpenMP, maybe not. But let's talk about how we can recreate this using Raja. So Raja for all is a template function that launches a parallel for loop. And it takes two important arguments. One is an iteration space argument. That's the first argument. The second argument is a lambda. So lambda is a C++11 concept, and it's basically just a function that's defined inline inside of another function and is anonymous. So you might be familiar with this from Python. These are used in Python. C++'s syntax is a little bit different from Python syntax. Let's talk about the iteration space object first. It's a little simpler. So as you can see in the README, if we have a very basic iteration space, like in that OpenMP example, which is just a half open interval from 0 to n, We can create a Raja type segment that represents that same half open interval and pass that as our iteration space in order to recreate that OpenMP example. The lambda is a little bit more complicated. This is standard syntax for a C++11 style lambda. The equal sign in the square brackets to begin the lambda indicates that we're going to capture arguments by value, which basically means that if we declare, you can see on the left-hand panel, this lambda, which is passed as the second argument to Raja for all, is going to capture values like n with a copy instead of capturing them by reference. We could also change this to an ampersand and it would copy values by reference, but we wouldn't want to do that because then we would be modifying the values of these variables that are declared outside of the lambda. So we're going to go look at this sequential Raja for all now. So you see, there's one more thing that we didn't talk about over on the README panel, and that's this template parameter, Raja sequential exec. So the Raja for all requires you specify where you want the for all to actually take place. In this case, seek exec just indicates that we're going to execute a sequential kernel on the CPU. And you see our data parallel kernel is very basic. We're just going to set the ith member of this array to I from 0 to n, exclusive of n. And so what we want to do is we want to implement this for OpenMP to recreate that pragma example from earlier. So in this case, it's very simple. We have another data buffer allocated for this example here using the same syntax that Christy just showed us. And we also have the identical space from 0 to n, iteration space. We capture variables in the same way in the lambda. The only difference is that we specify Raja OpenMP parallel for exec as the only template parameter to the Raja for all. And let's just give this example a little spin. And we can see that we get some speed up with OpenMP, but we don't quite hit that desired threshold of the sequential time over the number of cores. And the reason for that is that the amount of time it takes to manage the thread pool, create and destroy threads is comparable to the amount of work in the actual kernel itself. There are a couple other things going on that we don't have to get into as well. But yeah, this isn't a great example of how to reach that optimal throughput that we described in the slides. But this is a basic example of how to parallelize a Raja for all. So I'm gonna pass the torch here.
So we're going to talk about Raja reductions. And in the previous lesson that John just went over, we looked at a data parallel loop. But each of the loop iterates was independent of the others. We were just setting array values to different values. Anyway, in this lesson, we'll consider kernels that are not data parallel, meaning that there are data dependencies between the loop iterates. And this is dangerous because if multiple threads write to the same memory location, then we can get a data race or a race condition. And we can also produce non-deterministic results, and the results can be dependent on the order of operations that occur. So in this example here, we have a summation within a for loop within an OpenMP parallel for pragma. And this is dangerous because n threads are running all simultaneously, and there are n values being written to some at the same time. And at any point in time, multiple threads can overwrite the sum value at the same time, getting the wrong result. So To solve this in OpenMP, we typically use the reduction clause. We add a reduction clause on sum to the pragma. And this allows one thread to write to sum at any given point in time. And that kind of helps it helps solidify the solution to sum, right? However, this can still result in uh, accuracy of the summation because the ordering of the threads adding together a double is not guaranteed. And so we might get minor differences in some of the decimal points. This is all good for OpenMP, but it's important to note that not all parallel programming models have parallel reduction constructs. CUDA and HIP and SYCL do not have these sort of reduction constructs, and Raja provides a generalized reduction construct that you can apply to CUDA HIP, OpenMP, and other things. So in the lesson that I'll go over, we'll go over the Raja reduce sum object, and the particular lesson will look at speeding up or reducing a Riemann approximation of pi. So the basic reduction sum object syntax is as follows. We create a pi Raja reduce sum variable. We have to pass in a reduction policy, which determines what platform it runs on. And we give it the data type, which is a double. And we give it an initial value, in this case, 0. So with that, let me go to the actual lesson. So this is a sequential implementation of the Riemann pi approximation. And we see that we have the reduce sum object on line 18. Then we call it pi. And the for all that it's associated with has on line 20, has a Raja sequential execution policy. And hence, the reduce sum object needs to be instantiated with the sequential reduce policy. Right? We pass in the loop iterate, which is a type range segment from 0 to n, not inclusive, and then we have the loop body. And it's important to note also that after the for all runs, we obtain the summation by calling get on line 24 on the pi reduce sum object. And that allows us to get the actual answer. Right? So this is the sequential version of the pi approximation that is already given to you. The task in the lesson is to write the OpenMP version of this. And this is what it looks like. It looks basically the same. The loop body is the same. The only difference is that the for all execution policy is OpenMP parallel for exec, right? And hence the reduce sum object needs to be instantiated with an OpenMP reduce policy for pi. We call the same pi.get afterward to get the answer, right? And let's see how this actually runs and works for us in real life. Right, so the sequential approximation gets one answer. The OpenMP pi approximation gets an answer that's close, but it differs at some point because of the ordering of threads is not the same as the sequential approximation. Any questions about this as we move on to the next lesson? Okay, I think Christy
Yes.
will talk more about Umpire.
Okay, so in lesson 6, we will be going over host and device memory, and then how to get the Raja for all prepared for working on the GPU. essentially, we want to figure out how to actually start using the GPUs now with Raja and Umpire. So first off, each computer system has its own distinct place in which the system will really allow you to allocate memory. The GPU systems have distinct processors and memory spaces. So we have the host, which will refer to the CPU, and then the device, which we referred to for the GPU. And we use these terms all the time, and we've probably already referred to the device, but we really mean the GPU for the device, CPU for the host. So the host and device memory spaces are physically separate, and data has to be copied between them. So understanding how to manage these different memory types is really important for efficient GPU programming. And a lot of GPU programming models will provide routines to allocate and deallocate memory in either space and then copy between the spaces. So when you are programming any kind of, let's say, CUDA program, typically you have to allocate and initialize that memory on the CPU, on the host, and then you copy that initialized data to the GPU. You launch some kernel on the GPU to actually do the computations. And then once the GPU has the final answer, it would then be copied back to the CPU so that you can look at it and deal with that answer from there, whatever your application is doing. So in Umpire's world, these distinct places where memory allocation can be done are what we call memory resources. A memory resource can correspond to a hardware resource, but can also be used to identify memory with particular access or performance characteristics. So a good example of this is like pinned memory on a GPU system, or perhaps unified memory. Those are all memory resources that we have. And then Umpire creates predefined allocators for each available resource on a system, which is propagated when you do your build configuration. So for this particular lesson, lesson 6, the two memory resources that we will be dealing with are host in all caps for a CPU memory, which will translate to like a system malloc, and then device for, well, device memory. So if you did your build configuration for a CUDA backend device, this would translate to a CUDA malloc. And then you can use this double colon suffix. If you have a system that has more than one device, you can say, you can get an allocator for device and then double colon 0 or device double colon 1 to differentiate which device you actually want that memory to be allocated on. But by default, you can just use device and then it'll figure it out. So these are some of the memory resources that Umpire offers. There's a full list at the bottom of the README. But the next thing that we will look at is how to use Umpire's operations to copy data between the CPU and the GPU memory in a portable way. So you'll see that there are some to-do statements where you have to get the allocator for the device and then get the allocator for the host. And then we want to initialize that data on the CPU, but then at that point, we want to do our computations on the GPU. So we'll use an Umpire operator to do that. Back in lesson 3, we learned about Umpire's memset operator. But this time around, we will use the copy operator. So that is going to look like this signature here. So it'll take the destination pointer first, and then the source, and then some size that you want to copy. So the destination will be the GPU, the source will be the CPU, and then the size of the memory that we've allocated. And you'll see this in the to-do comments in the lesson. Yeah, so but then that's not all. We also want to adjust the Raja for all to now work on the GPU. So in order for this to happen, we need to do a few extra things to the Raja for all. And the first thing we want to do is create a CUDA block size. So at the very top of the lesson, you'll see that there's this new CUDA block size. And you can give it, a couple of values, but we recommend 256. That tends to be the magic number, essentially because there are 32 threads in a warp, and that's closely tied to the GPU architecture, and it just kind of works. But depending on your GPU, you may find that 128 or 512 might work better. But for most GPUs that we deal with, 256 is just a really good number. But then the Raja for all that is doing the computations needs to have the CUDA exec policy. So that's going to look like this. And then we will specialize it with the CUDA block size variable that we created. And then for the lambda expression inside the Raja for all, we also need to specify where that resides in GPU memory. And you can either use the explicit _ device _ annotation, or you can just use this Raja device macro. So I can show you what this looks like. Again, remember to uncomment out this compile thing so that it will actually compile. But then, yeah, we set up our CUDA block size. We give it that 256. And then we come down here. We use the resource manager to get an allocator with the device memory resource and then with the host memory resource. And then we allocate some memory. So if it's A_H or B_H, that is just a way to differentiate the host memory that we're allocating. So this is our first Raja for all that uses the sequential execution policy. And we're just going to simply initialize it with 1.0. But yeah, so this is all being done on the host in CPU memory. So once we have that, now we want to give that memory, that initialized data to the GPU. So we have our resource manager and we use the copy operator. Like I mentioned before, the first parameter is going to be the GPU pointer, and that's going to be the destination. The source will be our host pointer, and then we'll give it the size that we've allocated above to copy over. We also want to create our Raja reduce sum. So just because we're doing the dot product We want to make sure that we have our CUDA reduced sum ready to go. And of course, this time around, the Raja reduced sum will correspond to this Raja CUDA reduce, so that the policy for the reduction matches you know where that reduction will happen. And then we're dealing with doubles, so put that in, and then initialize it to 0.0. Okay, and then we are going to look at our cool and awesome GPUified for all. So like we mentioned before, this is going to take our the CUDA exec. We're going to give it our CUDA block size, which corresponds to 256, the magic number. And this is where we specify this Raja device. All that's really doing is telling the GPU that this kernel, this Lambda body thing, is going to reside in global memory space on the GPU, so that every thread is able to see this this Lambda expression. So yeah, Raja device. And then, we're doing stuff like before, and we will get our dot product, and then we deallocate our memory because we are good programmers, and we deallocate the memory that we allocate. Okay. And then we're going to test this, and well, bam. So very simple dot product, since we just initialized all the data to 1. But yeah. So this lesson kind of covered quite a bit. But if you have any questions, put them in the chat, and we'll have people looking at the chat to answer questions. And with that, we will move on to the next lesson.
Yeah, so we're going to talk about some of the built-in Raja algorithms in this lesson. So in previous lessons, I guess the first thing I talked about was data parallel kernels, where there's essentially no dependence between different iterations of the parallel for loop. We also talked about reductions, where each iteration of the parallel loop needs to add to the same value, essentially, in order to perform the reduction. And in this lesson, we're going to talk about 2 other examples where there's seemingly a lot of dependencies between different iterations of the for loops, and it might not be immediately obvious how to parallelize them using the constructs we've talked about. So the first example of that we're going to look at is atomic operations, which is probably familiar to a lot of folks. An atomic operation is essentially just something that allows multiple threads to access the exact same location in memory without creating a data race. And a data race, for people that aren't familiar, is where you have multiple threads trying to access the exact same memory at the exact same time. And what this leads to is there's a memory hierarchy in any processor, GPU or CPU. And what this leads to is essentially incorrect copies of that data at different levels of the memory hierarchy, and it creates undefined behavior. So we want to avoid that. That's a big challenge in parallel programming. And an atomic operation locks that location in memory when one thread is reading or writing from it, and basically forces all the other threads to wait in line behind it while it does whatever it's going to do to that memory location, read or write, and then unlocks it when it's done. Then the next guy can come up. There's a variety of ways that these locks can be implemented that are very hardware dependent, but that's the basic structure of an atomic operation. And to sort of demonstrate this, we're going to go back to the reduction in lesson 5, and that Riemann sum where we were trying to estimate pi. So if you'll remember, in that lesson we declared this reduced sum type object pi, captured it, inside of in the lambda, and we could just transparently add to it, like and under the covers, Raja reduce sum kind of automatically takes care of the fact that you have multiple threads doing things at the same time. A more, I guess, transparent way to implement the same thing but less performant is to use atomic memory access patterns to do the exact same thing. So you can see, let's go back to OpenMP here on the left-hand panel. You can see we have our, our integrand here, and where we had our just an add operation to pi. Now we're going to access that memory location using Raja namespace atomic add. Now this atomic policy is going to be backend specific. In our case with OpenMP, it's going to be OpenMP underscore atomic. And this is just the execution policy that we talked about earlier, that template parameter that we always need anytime we invoke Raja for all. And these atomic operations are really simple. We have Raja atomic add. We also have Raja atomic min, max. And all we're going to do is just feed it that atomic policy as its only template parameter. The first argument is going to be the memory location that we're trying to operate on in an atomic manner. And the second argument is going to be what we're going to combine with that location. So in our case, we're just going to add to it. This is what we're going to add to pi. And again, we have to multiply by 4 at the end because we're just integrating under a 1/4 of a circle. So that's how things work on OpenMP. We talked in last lesson about allocating memory on CUDA. So let's look about how this would work in a CUDA backend, just to reinforce the sort of syntax of Raja atomic add. So we can go down, and we remember Christy talked about device allocators. So because our pi approximation is going to live on the device, we need to actually allocate its memory on the device. Before we were allocating arrays, we're just going to allocate a single value, a single double on the device. So you can see here, we call our device allocator with allocate. Since we're just allocating a single value, it's just 1 times size of double is the amount of data that we're trying to allocate with the allocator. We need that static cast again. And then, yeah, we want to set it equal to 0, because if we don't do that, we're allocating heap memory. So if we don't set it equal to 0, we're going to end up with some garbage value as the initial value for our pi approximation, which will give us non-deterministic behavior most likely. So here we have the exact same kernel from above. We're doing the same things. We're doing this Riemann sum where we're adding to pi atomically, but we have a couple of key differences. One, we've annotated this lambda with underscore underscore device underscore underscore, which is a CUDA function annotation that lets the compiler know that this lambda is basically going to live on the device. It's going to be called on the device. It lives in device memory. It's very important to do that anytime you have a lambda that you want executed on device. You also might see host device that would allow it to be executed on either. For our execution policy, we're going to pass CUDA exec, which, as Christy said, is block size dependent. It takes one integral template parameter, which is the block size, which again, usually we would default to using 256. And again, the point of this lesson is we're going to use atomic add to access this pi approximation on device. And we have to use a different atomic policy, CUDA atomic. So yeah, let's run this example and see how it works. Okay, we can see we're getting relatively close approximations between OpenMP and CUDA. are there any questions about this example? This is pretty straightforward. It's just the usage of this Raja atomic add, and the only real thing you need to know is the order of the arguments and the atomic policy. Let's talk about another example of a parallel operation that is seemingly very hard to parallelize. Let's talk about scan operations. So a scan operation is basically you have an array as an input, and a scan takes an array combined with some binary operation like less than, greater than, addition, and essentially combines each element in that array element wise to create the result. So the most basic example is a parallel prefix sum, which would be an example of combining an array with addition. So, we have this example here below where we take this as our input array and the prefix sum output is here. So you can see the second element in the output is 7. It's 7 in an inclusive prefix sum because we've added 8 and -1, so we get 7. Now we look at the next element. It's 9. Okay, it's 9 because we've added 2 to 7, which is the previous element. So you can see that it produces this output in this manner. And when you get to the nth element in an inclusive prefix scan, you're going to essentially just have the sum of elements 0 up to n in the input array. So that's what a scan is. Now, on the surface, this might seem really hard to parallelize. There are a number of efficient parallel algorithms for this. Usually they rely on reduction tree structures. We don't have to get into that, but there are some good resources out there on the internet here. There's a lot of good examples of how this gets implemented in CUDA. We implement a version of this when we do reductions in example 5 under the hoods. That's how Raja reductions work, is using a reduction tree structure. But anyway, the good news is that we don't have to worry about that as Raja users because we can use these Raja inclusive scan and Raja exclusive scan methods to perform a scan. So let's just talk briefly about what the exclusive scan is because it's a little bit different. You can see that these array elements are mostly the same here, but there's this extra element at the beginning of the array. That's because the exclusive part of the exclusive scan just means that when you're at the ith element in the array, in the example of, say, a prefix sum, you wouldn't include the ith element of the input array in the result. So when you're at the 0th element in the array, you essentially haven't done any additions yet. When you're at the first element of the output array, you're just including one element from the input array, 8. When you're at the second element of the output array, you've just added 8 and -1. Essentially, the exclusive term just means that you're doing all of the additions up to the ith slot in the input array. Anyway, it's basically the same thing, but we have two different calls for it. So you can see that we take an exec policy here when we do an inclusive scan. That's because we need to specify, like, are we going to do this in OpenMP? Are we going to do this in CUDA? Are we going to do this on a HIP device? Those execution policies are actually going to be the same as the for all execution policies. So for CUDA, it's going to be CUDA_exec. For OpenMP, you can see over here, we're going to use OpenMP parallel for exec. And we also are going to combine this with a Raja span object, which is made with the factory function Raja make span. And what all the span does is it packages an input pointer with an integer to tell you how long that input pointer is in memory. And that input pointer could live on the device. It could live on the host, going back to our earlier lesson about memory. So yeah, these are the basic usages of these two methods. You can see over here on our scan example, you can see this, I guess, in a brighter font. You can also perform the same operation in place. You can just specify a single make span with an input pointer and an integer n. Let's talk a little bit about how to do this on CUDA. It's going to be pretty similar to the examples we've looked at earlier. We're going to need a device allocator. We're going to need a CUDA exec policy that depends on that block size that we talked about earlier. And other than that, it's going to look really similar to our OpenMP example. That's kind of the whole point of Raja. So you can see our scan, our exclusive scan in place. If we want it to happen on CUDA device, we pass in CUDA exec with the integral parameter passed as its first argument. And we make two spans, or this is in place, so we just make one span. This array underscore D is going to be a pointer to device memory, which is very important. If you tried to pass a pointer to host memory here, you would get a seg fault from Raja because we would launch a GPU kernel that tries to access memory that it doesn't have access to. And this operator maximum with the integral template parameter just refers to the way that that binary operation that we talked about earlier. So in this case, we're going to be sorting the array with a maximum operation. So let's run this and see what happens, see how it works. So you can see, just like in our example, this difference between inclusive and exclusive scans that are happening on OpenMP. And then if we go to this output, inclusive in place, this comes from this example where we performed the operation on the same input array that we did the inclusive versus exclusive scans. You can see it's the exact same as the output as the first inclusive scan because we're performing the same element-wise operation, addition, and we're just doing it on memory in place. And now if we go to this example, you can see the array in this example is going to have values equal to the index -1. So our input array in the CUDA example, the 0th element is going to be -1, the second element is going to be 0. And you can see there's this value -21. This is the minimum number that a 32-bit wide integer can take. And the reason why it's the first element is it's basically the identity of this element-wise maximum operation. So because we did an exclusive scan, the 0th element in the array got replaced with that minus that minimum integer value. So if there are any more questions about this, I can check them out in the chat. But I want to let the lessons keep going. We have another Raja Umpire lesson coming up. So if you have any more questions about scans or atomics, feel free to message the chat and I can try to answer them.
Cool. Thanks, John. Okay, so next we will be doing lesson 8, which is my favorite because it's all about memory pools. So up until now, we have just been dealing with Umpire allocators where you just allocate some memory. You don't touch really that memory after you've allocated it or initialized it, and then you just deallocate it. And in a lot of actual applications, production codes, these allocators, you would be allocating memory and deallocating them quite often, especially in a simulation code where perhaps every time step you have to allocate some kind of temporary memory, which would then be subsequently deallocated after a cycle or whatever. So in more realistic applications, we use memory pools for when you frequently allocate and deallocate memory, because that can be quite costly, especially when you're making large allocations, and especially when you're trying to do all of that in these HPC environments, especially on GPU. So we have memory pools that can provide a more efficient way to allocate large chunks of memory or large amounts of memory. Um, and so I have this cool little picture here, which is a visual representation of a memory pool. Essentially, within your pool, you have lots of chunks or blocks of memory, and your pool is accessible by some underlying allocator that you have built your pool on top of. And so a memory pool is a type of allocation strategy. It's what we call the strategies within Umpire. And this just allows us to customize how data is obtained from the system. So we have lots of different memory pools, but we will be learning about Quick Pool. As the name suggests, it's pretty performant in most use cases. It's kind of a general use, good performing pool that we recommend most users start with. And then if you find that you have a particular allocation pattern in your application that it might benefit from these other types of pools. So for example, we have the fixed pool, and as its name implies, the allocation, all the allocations in a fixed pool are going to be of a fixed size. So if you know that your application is always going to need 1024 bytes with every allocation, then you could use the fixed pool and actually get better performance than quick pool. But, for this particular lesson, we just need to learn about quick pool. So the way you do that is you use the resource manager, like always, to make an allocator. This allocator is going to be of the quick pool strategy type. The first thing you want to give it is the pool name, and then you have this allocator that you're building it on top of. So in our lesson, the allocator that we build it on top of is going to be our the device allocator that we've created on line 25. So in effect, this will be a quick pool that is using device memory, and because it has the device memory resource, that would map to like a CUDA malloc, but it will be much more performant than actually just calling CUDA malloc. So yeah, there are a few other arguments you could pass, but just for this lesson, those are the two most important ones that are required. You can always check out our user guide to learn more about how you might customize that pool. When you are building this, just remember to put in the quick pool header file, and you'll definitely need that. And then make sure to uncomment out the compile. And then, yeah, you can make it and then build it. Yeah, that's pretty much all for this lesson. We do everything else pretty much the same. But one thing I wanted to call out here is you may find as you're using memory pools that you still need to kind of fine tune the memory pool performance. And with Umpire, we do this through coalescing heuristics. So I have this really cool picture. Okay, so you can imagine that if this is your pool, this, big block here, you have the blue color, which is your used um, portion of memory that's currently in use. And then you have these free blocks here. So in this particular situation, perhaps you made an allocation, it was a temporary allocation, and then you deallocated it, and that's why it is now an empty block. So we find that memory pools will suddenly have one portion of it that's used, and then the other portion of it is full of these free blocks. And now, let's say we have a new allocation. And if we didn't have what we call a coalescing heuristic, none of these free blocks are large enough to accommodate this new allocation. So because none of the free blocks are available, we have to grow the memory pool and put that allocation in the memory pool that we've, just grown to accommodate it. In the scenario where we do have what we call a coalescing heuristic, we can go ahead and deallocate all of these small free blocks and reallocate one large block. And then now this one large free block is big enough to accommodate the new allocation, and we can accommodate that new allocation without growing the memory pool. So the coalescing heuristics provided by Umpire are a powerful way to make sure that your memory pool is performant and managing the memory behind the scenes well. So you can play around with these heuristics, and you'll find that sometimes you can make the memory pool as fast as possible with the heuristics, and sometimes you can make it as memory efficient as possible with the coalescing heuristics. And they're not necessarily, the same, because a coalescing heuristic does involve a deallocation and a reallocation of blocks. So you don't want to do it too much, but you might find that you do need to do it a few times so you don't run out of memory. But anyway, okay, so just a quick note about that. If you want to learn more about coalescing heuristics, we definitely have some awesome documentation about that. But yeah, so we got the right answer. I would love to answer questions about memory pools and coalescing heuristics. So if anything is unclear, definitely post a question. And thanks. Next lesson.
Okay, hopefully people can see this. So I'm going to talk about Raja views. The standard way we use arrays is as a one-dimensional array, like seen here, double A, and then we allocate an array of m by n size, right? But sometimes it's a lot easier to use some sort of matrix notation in a 2D or 3D style or more. And a Raja view does that for us. It helps us do that by wrapping a pointer to enable indexing under the hood that follows one of these layout patterns. So here in the highlighted blue highlighted text on the top, we create a Raja view called a view. We tell it what type of data is underneath, which is a double. We give it a layout of dimension 2, and that just means we want to have a 2D view over something. And that something is the A array here. That's what we first pass in, a pointer to the array that we want. And then M and N are the extents of the layout dimensions that we want in each dimension. So M rows and N columns for this particular view. This type of indexing, as I said before, makes using our data simpler. We can just have row column accesses like seen here. Note that this is a use of Raja views within a standard for loop. You don't need to use a Raja for all or a Raja loop construct to use views. You can use it in your your normal C++ code. In the particular lesson that I'm going to go over, we also make use of a function called makePermutedView, which is just a function that gives you a view, so auto a view, and it provides you a little bit of a couple options for indexing styles. So in this makePermutedView, we're using layout right, and that just means the rightmost index, n, will be the unit stride or fastest moving index, and m will be the second slowest, or in this case, the slowest. And layout right has the same indexing as a standard view that you would create up on top. So this view on top has its fastest moving index as n and the slower moving index as m, just like layout right. So we also have layout left, as you can see here, which is like a Fortran style indexing where m would be the fastest moving index and n would be the slowest moving index. Okay, so with that, let me go to the actual lesson. Lesson 9 is probably better explained by just running the solution first. So I'll show you what this is. And in the lesson, we give you a layout left view of that has its elements, elemental values in this particular order. And you need to make a normal Raja view A match this ordering, and a right layout view R match the same ordering on the bottom here. So in the solution, of course, everything matches, and we're all good. So I'll go over really quickly how this lesson works. So this is just printing out the arrays. Okay, so first we want you to create a standard view A on the array lowercase a. You know, it has type double, and it has a layout of dimension 2 on top on line 41 here, and it's m by n dimensionality, right? We give you a permuted view that's using layout left, which is the end result array, and we want you to create another permuted view that's layout right, and that looks pretty much exactly the same as the layout left, except you just pass in the layout right type. Okay. So then we want you to fill in the loop bounds for setting A and R. So because they are A and R are both layout rights, then the fastest moving index is on the right, so it's the column. So column is in the inner for loop, and row is in the outer for loop. And then we set the values of the arrays to their index values. So we have to do the traditional indexing arithmetic to set the values, and they're the same for each one because they both have the same type of layout, just named differently. Okay, so that's the solution to that. This is how we're setting the layout left view. Note that the column and row ordering are different. Column is in the outer for loop, and row is in the inner for loop because row is the leftmost index for L, and it's the fastest moving one, so we have to have it as the inner for loop. And of course, the indexing calculation is different because it's a layout left. Right? And then the following is just looking at the output and making sure that everything matches the way we expect. Okay, I think that's the end of this lesson. So if you have any questions, you can ask them. Otherwise, we can move on to the launch lesson from John.
That's right. Hi again, everybody. Yeah, let's talk about hierarchical parallelism and how Raja supports it. So GPU programming models like CUDA, HIP, and SYCL, need to create abstractions in order to handle much larger numbers of threads than something like OpenMP. So, a typical GPU has thousands of threads on it compared to, a really big CPU might have like 64 threads. So because of that, these GPU programming models create abstractions like called a compute grid. And compute grid is just a logical structure that organizes threads into groups. And those groups are usually called blocks in CUDA or HIP. And in this example here, this diagram, we have a one-dimensional compute grid and we have one-dimensional blocks as well. But I bring this up because oftentimes CUDA and HIP, for example, allow users to provide up to three-dimensional blocks of threads and a three-dimensional compute grid. And this can be conceptually useful for developers when thinking about how to, say, do some computation on a three-dimensional mesh, for example. So yeah, just an overview of terms. The grid is a group of blocks. A block is a group of threads, and threads are that basic work unit that we have on the GPU. So there's different ways of once you're executing a program on an individual thread of placing that thread within the block. You can access the block number that you're currently in. You can access the dimension of the block, and you can also get the index of the thread within that block. Now, sometimes you might want to know what's my overall thread number, like within the entire, out of all the threads on the device, what number am I? And you can compute that using this global ID, block number times block dimension plus thread ID. This might be familiar for a lot of people who've done anything in CUDA, but I bring this up because it's useful for the example we're going to go over. Now, Raja has sort of internalized these concepts and defined this Raja launch function template. And we replace some of the terminology with our own Raja terminology. Instead of having blocks of threads, we call them teams of threads. We also have normally in a GPU, in CUDA or HIP, this launch would look completely differently, but we continue using our C++11 Lambda concepts in order to define the launch. So Raja launch needs a launch policy. That launch policy is going to be backend specific. It's going to take launch parameters as its first arguments. The launch parameters are going to define the number of teams and the number of threads. So if you're familiar with the triple chevron notation in CUDA, those would be those first two arguments that you pass inside the triple chevron are going to be passed to the Raja launch param argument, which is the first argument of Raja launch. We're going to have this outermost lambda, which is going to capture things using the copy operation, copy capture, and we're going to mark it as host device. And we mark it host device because this is equivalent to a CUDA kernel, like that you would mark __ global if you're familiar with CUDA. We also are going to pass as its only argument to the outermost lambda a Raja launch context type object. And the Raja launch context enables synchronization between threads in a team, shared memory access. The context basically gives us access to sort of some other CUDA features that you would think of, like synchronizing locally within a team. In this case, we're just looking at a one-dimensional grid structure. So there's only going to be one innermost loop, which is just a single Raja loop. And Raja loop accepts a loop policy, which again is going to be backend dependent. We're going to pass the context to that inner loop because again, we might need that to perform a synchronization inside of the Raja loop. And this is where we're going to define the actual ranges over which the loop operates. So again, we use that Raja range segment, which is familiar from our for all example. And another difference between this Raja loop call and the normal Raja launch call is that this innermost lambda, we're going to just capture things by reference. And that's important because if you think about it, let's say we want to perform some team synchronization inside of this innermost lambda. We want to be doing that on this launch context that is passed as an argument to the outermost lambda. We don't want to do that on a copy of that. We want to capture that context by reference to guarantee that we're sort of synchronizing correctly between different threads. So this is the basic structure of a Raja launch, and you can see it's inspired directly by different CUDA and HIP programming abstractions. So let's talk a little bit about policies. So these policies are what's going to be passed to Raja loop. And they need to be wrapped in a Raja loop policy type, but we'll get into that later. For now, we just need to look at these policies to try to understand. Let's say we want this integer I. We talked about different ways of thinking about a thread index within the overall structure of a group, right? So we talked about how we can just think about thread IDX. We talked about how we can think about the block index that we're in or block number. And accordingly, we provide policies for each of these different ways of thinking about index. So if you specified thread direct X, for example, to Raja loop, this integer would just get populated with thread index.x if you're compiling to a CUDA backend. If you provided CUDA global size X direct, you would get this full overall index into the global thread number. So, you'd be at like, if you had concretely, if you were creating 16 by 16 blocks of threads, the thread IDX, or actually, let's just say if you were creating 256 block size thread blocks, thread IDX.x would be between 0 and 255. But if you were doing that same block size and you passed a CUDA global size X direct, you would get, say, thread 4000, up to the greatest number of threads that exist on the device. So to make this a little more concrete, let's talk about a matrix transpose. Now, probably a lot of you are familiar with CUDA and familiar with hierarchical parallelism. And the way that we would handle a really big matrix transpose on a GPU is we would map the entire matrix onto the entire GPU in blocks of 16 by 16 blocks. So, we'd take like the first 16 by 16 subarray and map it onto block 0. We'd take the second 16 by 16 subarray, map it onto block 1, and so on and so forth. We've kind of passed into a two-dimensional grid here. This is a two-dimensional compute grid, but we talked about how you can have one-dimensional and two-dimensional compute grids earlier. So let's look at this example. We're kind of just going to run this example because we've already talked about a lot of the key components, but let's just point out a couple of features of this. So remember we talked about Raja launch parameters. So this is the first argument that's passed to Raja launch, and we're going to pass Raja teams, and we're also going to pass Raja threads to the launch parameters. And notice that teams is now taking 2 arguments and threads is taking 2 arguments because we're specifying a 2-dimensional thread team and also a 2-dimensional compute grid. We're going to also need these loop policies because we're going to have 2 nested inner loops according to our team dimension. And because we're mapping this entire big matrix onto the entire device, we're going to specify global size Y direct and global size X direct. If we were, say, doing a finite element calculation and we were mapping smaller arrays onto teams, we might use a local thread index. But anyway, let's run this example to see how it works. Okay, it's not very exciting, but you can see that we're doing this matrix transpose operation, swapping row for column, column for row. You can see these basic structures like the size of the compute grid, why we would choose a global size versus a local size versus a block size. There are many examples inside codes like, say, MFEM, where they would choose a completely different Raja policy to do this to do a Raja launch. And again, that's kind of specified by the problem that you're trying to map onto a hierarchical parallel architecture. So yeah, if you have any questions on this example, feel free to message the chat and I'll try to respond. But we're going to go into a demo now about how to use Caliper with Raja.
All right, thank you. And thanks everybody for sticking with us. So we are going to be looking at some live coding. I want to give a brief introduction on what I'm going to do, what Caliper is, and how I configured it. And if there's any questions, as before, feel free to ask on the chat. We have the WebEx chat and the Slack chat. So the purpose of this demo is to demonstrate how we can use Caliper within Raja to look at performance numbers. And once we identify what our bottleneck is, we can spend some time looking at different Raja policies, and we can figure out how we can accelerate our code. Just to double check, can everybody hear me? Everybody see what's on my screen?
Yes, I think it
Yes.
looks good.
Thank you. So in this demo, there's a file in the AWS instance called profileraja.cpp, and this file contains 3 linear algebra kernels. 2 of them are written with for all. The third one is written with launch. There's matrix addition, matrix scale and multiply, and matrix multiplication. So a little background on Caliper. Caliper is a profiling tool that's developed at Lawrence Livermore. A lot of the major codes use it to get runtime reports. It can be integrated with vendor tools. There's a lot of neat features that can be used to gather performance metrics, runtime reports, and there's a lot of companion software out there that can be used to process the data. Now, the purpose of this is not to do a full demonstration of all the Caliper capabilities, but really it's just a example how we can quickly get started integrating Caliper into Raja and getting some basic profile information. As a plug, so a full Caliper tutorial is going to be on Tuesday, August 26th from 9 a.m. to 12 p.m. Just like you registered for this tutorial, you can register for that tutorial. So here we'll be using Raja's Caliper plugin capability to generate runtime reports. And the way this works is you simply name your Raja kernels. So there's a construct called Raja name, and if you give it a string with the name of that kernel, it tells Caliper to profile that particular kernel. And I'll demonstrate how this works. Just a little background in case you're interested in configuring this at home. The way I configured Caliper here was I configured it for NVIDIA GPUs. I turned on NVTX, which is NVIDIA tools extension. So this means that Caliper regions become NVTX events. So this is useful for when you fire up the NVIDIA profiler, you'll be able to see the name you gave the Raja kernel on the profiler. Uh, and then I also turned on the NVIDIA CUDA Profiling Tools interface. So this will allow us to gather low-level CUDA performance metrics and report some other GPU activities. We won't be really diving into the NVIDIA profiler, but I just wanted to make that available if folks are interested in turning this on at home. Configuring Raja with Caliper is straightforward. All you have to do is configure the following CMake variables. You just tell Raja to enable Caliper, and you point to the Caliper directory. And in any application or file where you want the kernel naming capability to queue Caliper runtime reports, you just include this file, the Caliper plugin.cpp file, which is also available in the AWS instance. Now let's get started. So we have our code. If we were to run it with the following runtime variable, cali config equals runtime report, we'll get the following output. The Kali config is one of various predefined configurations that Caliper provides, and this is a way to look at your data. So the runtime report will give you the following 4 columns. The leftmost is the time reported in exclusive numbers. then you have inclusive, and then you have percentage in terms of exclusive and inclusive as well. So this file just has the functions all in the same, at the same level. That's why the exclusive and inclusive timings are the same. But from here, we can see that our hotspot is the matrix multiply kernel. So let's dive in. And then I just want to make a double check. And is the font size a good size? Should I make it larger?
Maybe larger on the terminal side. I don't know.
Is that better?
I think so.
Okay, cool. And I appreciate the questions. If one of my team members can help, that would be great while I do the tutorial. Or if it's something I should stop and we can discuss, I'm happy to do that too. Just let me know, and I'll be relying on my team members for that cue. So I want to do a quick tour of the profile raja.cpp file. What we have here are some basic configurations that you can use to invoke Caliper and Raja. So you have the basic runtime report. So the number I'm feeding at the end of the executable corresponds to the matrix size. So if I ask for 1024, I'll generate a 1024 by 1024 matrix. There's a quick check to make sure that the matrix multiply algorithm is correct. And then you have the 4 columns that we described before. There's other configurations that we can use. So there's this CUDA activity report. And what this will do is we'll generate a tree. And this tree will create 2 categories. It'll give you host time and GPU time. It'll tell you where you're spending your time on the GPU and the host. You'll have things like CUDA stream synchronize numbers, CUDA memcopy, CUDA get device, and CUDA free. So you can start looking at more details of how you're running the code. If you see these tildes, that means the name is pretty long, and that's how Caliper truncates the name of the function. Lastly, if you're interested in generating a file that the NVIDIA profiler can read, we have this example here. I've already, oops. Well, I'm missing a module here, but I've already created it on beforehand, and what we should get is something that looks like this. So if we dive in here, we can see the NVTX regions. We have matrix multiply. We have the initialization, the matrix addition, the scalar. And as we saw through the runtime report, the matrix multiply is our bottleneck. It's what's taking most of the runtime. I want to continue doing a quick tour of the code. We're going to be exploring 3 different policies for the Raja launch abstraction. We'll be looking at direct policies, something called loop policy, and then the global policy. So 2 of these John talked about a little bit beforehand. We have some const expression numbers, so we're using 256 threads. Launch max threads, I want to come back to this. This is a note to myself to come back and discuss. And we're turning off synchronization for we're making our kernels synchronous just to make sure we get the correct performance numbers. So CUDA kernels launch asynchronously. So if we're doing profiling while the kernels are set as to asynchronous mode, then we won't get the correct performance numbers. And here's my for all policy, and the launch policy is going to be CUDA. We're working on the CUDA interface. So as I mentioned, if you want to get profiling information, you just add the following attribute, the name attribute, and you pass in whatever string you're interested in. So we do this for the init, matrix addition, scalar multiply, and matrix multiply. So here we're using a lot of the machinery that was talked about during this tutorial, where we have the permuted views, and we have here 3 types. We have 3 different policies we'll be looking at. So the direct policy, the way this works is we're going to be mapping threads directly onto the rows and blocks directly onto the columns. Now, there's some limitations to this. For folks who are familiar with the CUDA programming model, they'll know that there's a max size of 1024 threads per block, which means that if I want to run something slightly larger, then we'll end up throwing an error due to a higher number of threads being requested than are than currently supported. So as an alternative, what we could do is we can add loop constructs to the threading. So what this means is for the columns in which we're mapping the threads directly onto, we can add a block stride loop. So if you have a matrix that exceeds the number of threads available, you can simply just recycle the threads until you match the iteration space. Likewise, for the blocks, you can add a grid stripe loop. So to turn this on, I'm just going to go to the top and uncomment the loop policy. And then I do have to rebuild this, make profile Raja. All right, great. So now we can multiply matrices that are larger by 10 than 24. So as we examine performance, it's quite common to want to increase the matrix size. So what we want to do here is see if we can create a much larger matrix to get a larger time. Oh, I didn't have to rebuild this. Okay, here we go. So let's make this a little larger. And then we don't have to build again, but we want the profiling. All right, so we're looking at a runtime of 5 seconds. So the third type of policy that we're going to try out is this global policy. And this is what John was talking about in his matrix transpose example. So here we're going to launch a 2-dimensional compute grid. And the compute grid is going to be composed of thread blocks that are 16 by 16. And we'll launch as many as we need so we can have a unique global index that will cover the output matrix. And then within the loops, we'll perform the associated dot products and we'll write out the solution. Here we have to build because I changed the source code. All right, so we shaved off a little bit of time. Let's see if we can do something a bit better. Let's go back to the loop policy and see if increasing the problem size will give us a bit bigger speed up. So let's see if we can run with 30,000. Oh no, I think maybe 20,000 might be our limit. So let's do this. All right, 12 seconds. So we'll come back to the global policy, and then we'll see how we do. All right, 11 seconds, almost a second. So I have an ace up my sleeve. So this launch max threads is actually going to help the compiler do some optimizations. What we're doing here with launch max threads is giving you're telling the API, you're giving it the maximum number of threads you're going to be using. And what this will allow it to do is do a better job optimizing for register space and other things. So let's see if we can get an improvement here. All right, 9.7. So that's significantly faster than we were doing before. So these are the type of tools that are available within Raja, within Caliper to help us identify bottlenecks and optimize our code. So I just kind of want to wrap up and bring it back to the presentation. So I just want to make a quick comparison of what we did right now. We investigated doing using 1D threads and blocks to perform the matrix multiplication to 2D grid block mapping. So one of the things we saw at the very beginning is that if we just do a very direct mapping, we're limited by the max threads and blocks. With 2D grid and block mapping, in practice, there's typically not much of a limit. We didn't look at occupancy here, but if you start investigating occupancy, then for the 2D grid mapping, you'll likely find that there's better occupancy. You, Once you start diving into more of the details, the 2D grid block mapping allows for more coalesced efficient reads. If you start doing some more ninja level optimization where you're introducing shared memory and tiling, then the 2D grid block mapping is definitely the way to go. And so I think for these reasons, the 2D grid block mapping ends up being a bit more flexible. I do want to also highlight a few things. I'm just showing here the browser. So this is the Caliper repository. It's in GitHub, LNL Caliper. There's documentation available and companion software, Hatch and Thicket. I do also want to make a shout out to the Raja cookbook. So a lot of times when we get started with Raja, maybe we're looking for common patterns that our code may have. So the Raja cookbook is a ever-growing resource that's going to include that has examples of how you can take your application and use Raja within it. So here's reduction with for all, and this is an active area where we're growing. So here's an example with what we call multi-reductions. Not covered here, but this is available. And with that, I'd like to conclude and open it up for questions if anybody has anything they want to discuss in particular or questions for the team.
There's a question about the Raja roadmap to add support for Apple GPUs. Oh. Any of y'all want to try to tackle that one?
I don't think that's really on our roadmap at the moment, because we cannot purchase them in bulk for our HPC needs at Lawrence Livermore. So yeah, I'm not sure that we'll support it in the near future.
Yeah, I think there was a comment earlier that a lot of the development priorities of Raja and Umpire are driven by, the labs, the program needs of the lab. And so that revolves around like the supercomputers that we house here, our HPC environments. And that is just pretty much NVIDIA systems and then AMD systems. And now, of course, with El Capitan, more heavily focused around AMD systems.
Right, that's correct what Christy said. And I guess there are two more comments, one by Parksheet I think it's more of a question of making development easier, and George says maybe through Sickle, the Apple Silicon can be supported. If Apple GPUs are, supported by the Sickle interface, then Raja already has a Sickle backend, and that could potentially work. But I don't know of such a development. Oh, good. Sickle currently only supports CPUs on Apple Silicon. Oh, I see. Okay. Okay. Yeah.
Yeah, I mean, I would say most of our GPU developers and most of the GPU development I've done, I use Livermore's on-premises resources for GPU development, and a lot of the micro optimizations involved in GPU programming kind of require access to the types of GPUs you're going to run an application in production on. So that is probably one reason why making it possible to develop on Apple GPUs is a little less of a priority.
Yeah, and I think Umpire's development priorities are going to strongly mirror Raja's. So yeah, our backend support, similar to Raja's, is the AMD devices, NVIDIA, and then Sickle devices as well. So yeah.